So we saw on the last homework and video that if you start with a Jordan set and you apply a linear transformation, what you get out at the end is a Jordan set. And what's more, I can write down a formula for the volume of the resulting Jordan set. So now what we're going to generalize this. So let's let X be a Jordan set. And phi is a function from X to Rp. We'll say we'll specify that X is a Jordan set in Rp. And now linear functions, that's very restrictive. So let's say continuously differentiable. And then the question is this still true? What can we say about phi of X? Is phi of X still a Jordan set? Can we write down a formula for its volume? And we'll need a couple of other technical requirements, but the answer in both cases is yes, but it's going to take us quite a while to get there. So here is the first lemma we're going to need. So let's let X be a subset of Q, be a subset of Rp, where X is a convex Jordan set, and Q is a cube. That means a rectangle where all the sides have the same length. That'll make this a little bit easier to state. By convex, I mean that if you have 2 points X and Y that are both in X, then the entire line segment in between X and Y is also in X. This line segment, you can write it algebraically as the set of all points X plus some positive less than 1 fraction of the vector from X to Y. All right, and now we let epsilon be a positive number, and then this set, the following set, this is the set of all points whose distance to X is less than epsilon. You can also think of that as the union over all points X in X of the balls centered at X of radius epsilon. It's contained in J, where this J is a Jordan set. And we can say something about the volume of J. X is certainly in this set of all points a distance less than epsilon to X because epsilon's greater than 0. So certainly the volume of J cannot be any smaller than the volume of X, but we can add an arbitrarily small amount. The side length of Q is a cube, so its side length is just the pth root of its volume. Then we add 2 epsilon to that. We raise the whole thing to the pth power. We subtract off the volume of Q, and we add epsilon to the p. What a mess. And no, it's one of those lemmas where it's very easy to draw a picture of how you do the proof, and then very hairy, very annoying to write out the algebra that actually works in all dimensions. So what I'm going to do is I'm just going to draw the picture of the proof. So here is our cube Q, and we make it bigger. We draw another cube around it that is padding is with epsilon. And so this whole region has volume. That annoying thing I wrote up at the top, the side length of Q plus 2 epsilon. It's a cube with that as its side length, so you take that to the pth power and subtract off the volume of Q. Now our set X is in here somewhere. And what we're going to do is, because X is Jordan, there is a cover, a rectangular cover, P of X, such that the volume, that's such that the upper sum of 1 over P will suppose that this is one of those covers where we throw out all the extraneous rectangles. That's less than the volume of X plus, we need a little bit of error. Let's call that error epsilon to the P. Let me draw this cover. And then we can refine in this cover, we can subdivide it that in a way that gives us a cover. We can just draw, we can break everything up into by drawing these horizontal and vertical lines, or it would be planes in the case of a three-dimensional cover. We just draw this refinement of the we just consider this set of rectangles. Then we keep all the rectangles that actually intersect X. That is not going to be a necessarily a convex set, but it's going to be convex in the horizontal and vertical in all the coordinate directions. So what you can do is you can grab this rectangle up here, these rectangles on the top, move them down, fill them in, grab this rectangle here that covers this region, this rectangle covers this region, this rectangle covers this region, and then do the same thing on the other side. This rectangle covers this region, this rectangle covers this region, this rectangle covers this region. So the idea is we can cover, I don't want to write that long description out. Let's name this set up here, or let's name it Y. So we can cover Y by a refinement of P and a set of rectangles of total volume at most our complicated expression side length of q plus 2 epsilon all to the pth power minus the volume of q. And we see the picture of what's going on. I don't want to write out the algebra of exactly how to make this work in arbitrary dimensions, so I'll ask you to let me just stop there. Here is the next proposition. Here's our next proposition. This proposition will tell us at least something about what continuously differentiable functions do to rectangles. So let's take a rectangle and let's remember from an early homework that differentiable functions on non-open sets aren't necessarily, the derivative isn't necessarily well defined, so let's just grab an open set containing R to be our domain for our function, which is continuously differentiable. And let's pick a point in R. The conclusion then is that phi of R, we can't say that it is a Jordan set, but it is we can't say that yet at least, but it is contained in a Jordan set where J is a Jordan set and the volume of our Jordan set, it's going to be what we saw in the previous lemma. The volume of the rectangle times the determinant of d phi of c. That's a familiar expression. That's the volume of d phi of c, which remember is a linear operator of R. And then we have to add to that a whole mess, the diameter of R to the pth power, and then we've got a long thing, a long expression, the norm of our linear operator plus 2 times the supremum over all points z in R, the operator norm of d phi of z minus d phi of c. If phi is continuously differentiable, we can make this quantity small by making the diameter of R small. And then we take the whole thing to the pth power, and then we have to subtract off it. It's complicated. D phi of c quantity to the pth power, and then we'll add on our supremum again. Whole thing to the pth power. So now let us prove the proposition using, of course, the lemma right above it. let's let X be this set. We'll take our linear operator d phi of c. Actually, why don't I give this linear operator a name? I'll call it A, which is a lot simpler to write. And let's let X be A of R minus C plus phi of C. This is the set of all points. Phi of C plus, I'll go back to calling it d phi of C for a moment because I think that will be helpful. Phi of C plus d phi of X minus C for all X in R. All right, now let's notice by the last video that A of R is Jordan with volume V of R times the determinant of A. That is where this V of R times the determinant of d phi of C, which is A, comes from. And X is a translation of A of R. X is A of R plus some constant vector, which as it happens is phi of C minus A of C. And it is an exercise. It is not particularly hard to show that X is also Jordan. With the same volume. That is, if you just add a constant to every point in a set, that's like moving that set, and unsurprisingly, it doesn't change the volume. Here is our claim. Here is a claim. My claim is that if Y is in phi of R, then Y is in some ball centered at X of radius epsilon, where X is a point in X, and epsilon is that horrible thing we saw above. It is the diameter of R times the supremum over Z in R d phi of C minus d phi of Z. And here is how we prove the claim. Let Y be a point in phi of R. Then Y is phi of X for some X in R. That's what phi of R means. Then now we're going to use homework 26. We saw in homework 26, among other things, if V is in RP, then there is a Z Z is on the line connecting X and C. R is a rectangle, so R is convex. That whole rectangle is, that whole line is in the rectangle. So Z is in R such that the inner product of V with phi of X minus phi of C is the inner product of V with d phi of Z evaluated at the point X minus C. This is the closest you get in higher dimensions to the mean value theorem. Remember, the inner product with V is a linear function. So if I feel like it, I can subtract off a constant here, d phi of C of X minus C. That's the inner product of V with then this thing minus this thing. And I'm going to put the linear functions, I'll group those in parentheses. And then of X minus C. And then we'll let V be just the whole this whole mess up here. Our phi of X minus phi of C minus our d phi of C, that's A of X minus C. Then, what can we say? The norm of V squared, that's the inner product of V with itself, which is the inner product of V with d phi of Z minus d phi of C. That linear function evaluated at X minus C. That's less than or equal to the norm of V times the norm of the rest of it. And this is by the Cauchy-Schwarz inequality. And that's less than or equal to the norm of V times the norm of our linear function. Times the norm of this X minus C. And that's the definition of the norm in L of Rp in the space of linear functions. We cancel out one of the norms of V, and we conclude that the distance from phi of X is Y minus this whole thing, A of X minus C plus phi of C, is less than or equal to X minus C over the diameter of R, our rectangle R. And then I really do not want to write this quantity again, so I will notice that it's less than epsilon, where we've defined our epsilon above. And then X and C are both in R, so this is so the distance between them is less than the diameter of R, so this is less than epsilon. But A of x minus c plus phi of c is in our set X. So that completes the proof. Here is our rectangle R. Here it has some point W in the middle of it. And then let's notice that and then if X is in W, then the distance from X to W is less than or equal to half the diameter of R. So our set X that's the set of all A of X plus phi of C minus A of C. That is contained in the ball centered at A of W minus C plus phi of C, with radius the norm of A times half the diameter of R, which is contained in Q, some Q, with volume being twice that radius times the diameter of R, all raised to the power of your dimension. And then if you put the claim together to get with this fact in the lemma, if you put it all together and check your algebra, I'm not going to write down the details. You can verify it for yourself. We've proved the proposition. Now, if we're going to want to put these all together, if we're going to want to look at continuously differentiable functions applied to arbitrary Jordan sets, we're going to need the following piece of notation. Let's let R be a rectangle. That is, it's the Cartesian product of p different closed intervals. And let's let L be the length of the shortest side. That's the minimum of the BK minus AKs, where K is between 1 and P. And then if the longest side, or we can put it a different way, every side, if it's at most twice the shortest side, we're going to call those nice rectangles. Nice is a nice short word, easy for me to write down. And this is not too restrictive. If you start out with a rectangle that is not nice, that's very long and thin, for example, you can cut it in half. If it's still not a nice rectangle, you cut it in half again. Eventually, you get to a nice rectangle, and it is an exercise in your book that if P is a rectangular cover, If X is a set and P is a rectangular cover of X, then there is a refinement of P, another rectangular cover that you get by slicing all the rectangles of P up like this, containing only nice rectangles. Well, and rectangles of volume 0. Those ones you cannot split up. Here is another lemma about Jordan sets we are going to need. We've proven a bunch of results this lecture about how about sets being contained inside Jordan sets. So let's see what we can do with that. Let's let X be a set that's contained in the union of some finite number, let's call it n, of Jordan sets. So each JK is a Jordan set. And let's let epsilon be a positive number. And the conclusion is that then there is a rectangular cover P of X such that the upper Darboux sum of 1 over P, that's the thing you have to take, remember, if you're trying to show that X is a Jordan set and find its volume, it's less than the sum of the volumes of the Jordan sets plus at the end an epsilon over 2. And maybe I'd better put the epsilon over 2 at the start, actually, to make it clear the epsilon over 2 is not inside the sum. So to prove this, it's not terrible. Let's let PK be a rectangular cover of our Jordan set JK such that, first of all, it doesn't have any redundant rectangles if R is in PK, then R actually intersects JK, and the upper Darboux sum of 1 over PK, we can make this as close to the volume of JK as we want. The condition where R has to actually intersect PK, it means I can write this upper sum as follows, and I don't have any leftover terms. I don't have to specify R intersects J. I can make this as small as I want. I want it to be at most the volume of JK plus a little error. My error will be epsilon over 2n. All right. Then the union of the PKs is a collection of finitely many rectangles. And if you have finitely many rectangles, even if they overlap, you can cut them up in such a way you can produce basically it's a refinement of each of the rectangles. This is one of the lemmas I gave to you back in section 7.2. So there is a collection. I'll call it P1 of non-overlapping rectangles. Such that no, I don't want to call it P1. I'm going to call it P-twiddle. I'm using P1 for the cover of J1, such that if R is in one of the PKs, then what is true? Then R is the union of all the rectangles. I'll call them C in P-twiddle. All the rectangles in P-twiddle that are contained in R. And just in case, let's make it an explicit threat step that we throw out all the superfluous rectangles. So we're going to take only rectangles contained in one of those R's. And notice that throwing out superfluous rectangles, we still have that R any rectangle. We haven't thrown out any of the rectangles that are contained in R. So we still have this property even for C even for P instead of P-twiddle. And also, if X is in X, then X is in JK for some K. So X is in R for some R in R cover PK. R is the union of some rectangles in P. So X is in C for some C. So P is a rectangular cover of X. All right, and finally, the upper sum of 1 over P, that's the sum over C in P, the volume of C. I suppose we do have to specify C intersect X is not empty. That's what the upper sum of 1 comes out to. That's certainly less than or equal to the sum of all the volumes where we don't throw away with the ones that don't see C. And then every C in P, it's contained in one of the R's, and every R is in one of the K's. So this is less than or equal to from K equals 1 to N, that's sum over R in PK, and then sum over C in R, the volume of C. we might be double counting, which is why this is an inequality. C might be in more than one of the R's, but it's in at least one of the R's, so we can't be missing anything. And then the C's in R, they're non-overlapping rectangles. We can turn this into the volume of R. And then that is just sum from k equals 1 to n. The sum over R and pk, that's the upper sum of 1 over pk, which is less than or equal to the volume of jk plus an epsilon over 2n. Sum that last piece from k equals 1 to n, you get your epsilon over 2, which is what we wanted. So here is the change of variables theorem. This is really the point of section 7.4. We'll get to the proof of it in the next video, I hope. So let's let X be a Jordan set, a compact Jordan set. That compactness requirement is not actually all that terrible. Jordan sets are always bounded. If it's not compact, you take the closure. The closure, you just throw in the boundary, which is a set of volume 0. So all Jordan sets are pretty close to be compact. Now let's suppose there is an open set that contains X. And let's let phi be a set whose domain is all of G, goes from G to Rp, be continuously differentiable. And we're going to suppose furthermore that phi is 1-to-1. Maybe not everywhere in G, not even everywhere in X, but on the interior of X. So here's what you are allowed. You're allowed to have a situation like this. Your half pi, most of a pi piece maps to the whole circle. And it is okay if, say, this line gets double counted, is the image of both this boundary component and this boundary component. That is okay. What is not allowed would be if you went too far around. If you have overlaps that if your interior has any overlaps, if this piece goes here, this piece goes here, and then all this stuff in the middle, this interior stuff, comes from both this wedge and this wedge. That is what is not allowed. Conclusion is that then phi of X is also a Jordan set. And I can tell you its volume. The volume of phi of X. It's the integral over X of the absolute value of the determinant of that d phi of X, dv of X.